indicate that 0, -3, which should be right there. Now these things can be a little bit difficult to understand which values will be on the graph and which ones will not be on the graph. Well, excuse me, these two values will definitely be on the graph. What I mean to say is that the shape of the thing can be a little bit interesting to figure out. So I like to use a graphing calculator at this point. And if you take a look right here, this is what it's going to look like. This is in Zoom 6, so I'll go ahead and do Zoom 5 for you. Zoom 5 is Zoom Square, and what that'll do is it'll make your tick marks on the actual graph spaced out evenly, so this will give us a little bit better picture. So what's happening is we have a vertical asymptote here and a horizontal asymptote right here, just like we have in the graph on the left-hand side. An interesting thing to note is this graph will be symmetric. So if we wanted to plot some more points, we actually could look at the symmetry of this, and if this is our beginning point, it's not the origin of the coordinate plane, but you can kind of think of it like that. If we go right 3 and down 4, we should go left 3 and up 4, and that should be on the graph. And to verify that, you can type in your calculator an x value of -6. So we could go to calculate value and -6, and it should be up 5. So we've got left 6, and sure enough, there it is, up 5. We could do the same thing with this point, but it's going to be off the graph, so it's not really necessary. The more points you graph, the more accurate your graph will be, but for what we're doing here for this function analysis, these points and these asymptotes will be good enough. And we're just going to try to make it look like this graph does here. So let me see here if I can get it pretty close. Remember to hit all of your points. It's important to do that. And so we've got a nice picture of what our graph might look like here. There's a couple other things that we need to do when we talk about function analysis. So what I'm going to do is I'm going to move this up a little bit. We've got some extra room to write down here, and then we'll keep referencing the graph here at the top. Hopefully you can see that. One thing we need to do is we need to talk about end behavior. So end behavior is just what the y values, or the up and the down direction, what those values are doing as x gets super big and also very, very negative. So to indicate that, we're going to do the right-hand end behavior, the right end behavior first, and that's as x approaches infinity. As x approaches infinity, well, that'll get us to the right-hand side of the graph. The end of this graph, and we can use a of x if you'd like, that's the function notation, y is acceptable. However, our original function was given in a of x, so it's nice to use that same terminology, or same symbols, and we can do this little line here which means approaching. So as x approaches infinity, a of x approaches, and we can see that this green graph will approach this asymptote here, this horizontal asymptote, but it won't go across it. And so the value as x gets super, super big, this graph will continue to rise and climb and get very, very close to +1. And again, that's just your horizontal asymptote. We can do the same thing for the left-hand side. This time x has to approach -infinity as we go all the way to the left. And a of x then actually will approach the same thing. So this graph will descend and keep getting close to the value of 1. So remember, we want to state x approaches infinity, x approaches -infinity, that's always the same. And then on the right-hand side we can use y, or if there's function symbology used, we could use that as well. The next thing to do is find our domain and our range. The domain are all the possible values of x, and I kind of made a whoopsie when I graphed here. I'm not supposed to put a point when x is -2, so maybe I should draw something like this right here. That would be appropriate. This graph would come up to, and then there would be a point missing here. So the domain, we need to think about the possible values of x. The possible values of x are really any real number except x cannot be -2 or x cannot be -3. If we look at the equation, when we factor this denominator, we can just set each one of those equal to 0, and that would give us those two values of -3 and -2. We can't have division by 0, so the values of x that produce division by 0 are not allowed. We don't want to include those in the domain. If we go from left to right then in interval notation, the domain would be -infinity up to, but not including -3. We'll always write the union symbol. Then -3 to -2, again not including -2. We'll write the union symbol again, and then we'll go -2 all the way to infinity. If we look at this interval notation right here, we're excluding two values. We're excluding -3. We don't want to write the brackets. And then here we don't want to write brackets. We want to exclude -2, but anything else will work. You can also do this in set builder notation, but for now interval notation will be fine. The next thing we can do is we can talk about the range of this function. So the range of this function are all the possible values of y. So if we look at the graph, just come back down here for you, the graph exists at just about every single value of y except two of them. So there's this value right here, which is 1, so we don't want to include 1. And we have this other value right here. And now that you know a little bit about limits, we're going to take a look at a table and see what value we think that graph gets close to. So if we go back, we can go ahead and go to your table set. We're going to be investigating -2. We need to find that value of y that's kind of like missing there, because the graph won't actually exist there. The delta table, you can do 0.01 or 0.001, whatever helps you figure this one out. So if we go back to our table, we can look here, and right around there we've got like -11 it looks like, but I don't know about you, but for me these two values, I want them to be closer so I can actually figure out what is happening at that point. So we can just do the table set again and go another 0.1, so like 0.001, go to the table, and we can go, oops, got to go back to the table set, start us at -2. And we'll go to the table here, and it does look like the function is getting close to -11. So when we write our range, we're going to write -infinity to -11, union -11 to 1, union 1 to infinity. Again, we're excluding -11. No matter what we do, we can't make this graph actually equal -11 or the output equal -11, and then also 1 will not work here either. If you're thinking about some of your limit work, and if you've done some algebra with your limits, we can also look at this factored form, and we can take a look at what would happen when x plus 2 got canceled out and we substituted in that value x, which is -2. So when we do that, we'd have -2 minus 9 in the numerator, which is -11, and then -2 plus 3 is 1 in the denominator, so we'd have -11 divided by 1, which is -11. So not only graphically, you can see here that this graph looks like it's getting close to -11 at that point from either side. We looked at the table view, and then also in this case we can figure it out algebraically as well, and that's where that value of -11 comes from.